Hello, everybody. Hello. I hope you're all well. And we're going to do our lecture on nuclear magnetic resonance today. Audio seems to be working, and we will start right now. And here we are looking at nuclear magnetic resonance. Let's break down these three words. What is special about the nucleus that allows nuclear magnetic resonance to happen? Well, the nucleus is where protons live. What do you need to know about magnets to be successful in your understanding of Chapter 13? Well, we don't need much physics background. In fact, we don't need any at all. We just need to know some basic facts about magnets, and we'll review those shortly. The resonance here is not to be confused with the resonance you learned back in 241, where electrons were resonating within a structure and giving alternate resonance forms. The concept of the word resonance has to do with alternating between different states. Here we're not talking about electron states, we're talking about spin states of our protons. So going back, protons, if you recall, are either spinning clockwise or counterclockwise. And we can cause that spin to change if there's a difference in energy between spinning clockwise or counterclockwise. And there's normally not a difference in energy. So let's talk about nuclear magnetic resonance with magnets. Most of you in your youth played with magnets. Not all of you, I would assume. But if you had the traditional magnet that had a north and a south pole, and you had them where the north pole of magnet number 1 was lined up with the north pole of magnet number 2, you probably remember that they would come together in an attractive arrangement. So what happened there was the magnets zipped close together because they were attracted to each other. And in terms of energy, let's talk about the potential energy of the two magnetic fields. They both got more stable because of that attraction between the two poles. The magnets now have a more stable potential energy because their poles are lined up. So we started with the potential energy here. I don't know if you can see the yellow line there. And it went down because it became more stable. Here's the green line through the middle of these two magnets. And this change in energy is the amount of stabilization we observed from the normal state. Now, if I took my two magnets and had the poles misaligned or in opposition to each other, then they would repel each other. You couldn't get those magnets to be close to each other. If you, when you were young, you did that, they kind of just jumped apart. Why? Well, because, oh, I'm getting an echo here. They jumped apart because their spin states repelled each other, and both magnets now have a less stable potential energy because their poles are misaligned. Okay, so the energy went up, indicating this arrangement is less stable than when the potential energy went down. Okay, we're going to jump over to the textbook right now. Let's see how easy that is. I'm going to grab a piece off screen here from the textbook. Sorry, I'm using the wrong program. Here we go. I'm going to steal some stuff here, and we'll put it over here. Here we go. This is some facts about magnets and what causes magnetic fields. There's two ways to cause a magnetic field. One is to have a rotating charge, or another way is to cause charges to accelerate. You can make them accelerate linearly and still cause a magnetic field, but we will not focus on that. We'll focus on rotating charges. Magnetic fields influence other magnetic fields, just like we depicted over here. And protons are always spinning. That's something we knew from way back when. So normally, half of your protons in a nucleus are spinning clockwise, and half of them are rotating counterclockwise. And because the world we live in isn't surrounded by a large magnet, the energy of the two states is identical before we influence them with a magnetic field. Okay, and the prediction of the direction of this magnetic field is accomplished by using your right hand. So let's focus on this one right here, rotating counterclockwise. If your fingers are going around in this direction, and I'll try to show you in the little picture we have here with my face. Here I've got my hand, and my fingers indicate the rotation direction. So this is counterclockwise, and notice my thumb is sticking up. Okay, so a counterclockwise rotation indicates there will be a magnetic field that's pointing up. Now, if I have the rotation going clockwise, my hand has to go like this to get my fingers moving in a clockwise fashion. And notice my thumb is pointing down. Thumb pointing down. You'll never have to indicate this on a test for me. I just wanted you to know that you can predict the direction of a magnetic field just by following the direction of the spin. That's all you need to know. Okay, now there's a field of science called electron spin resonance, ESR, and the only thing that reverses there is that you have to use your left hand to predict the direction of the magnetic fields. ESR is the analytical technique, and we will not focus any time on it other than the time I just spent now. All right, normally the potential energies of the two spin states are identical, and this is a way of saying energies are identical. We call it degenerate. Means under normal circumstances, they're equal amounts of clockwise and counterclockwise spins. So let's go look at the book some more. I'll get better at this, I promise, right now. I'm just learning how to zoom back and forth. And we'll try this. I'm going to grab the potential energy diagrams found on the first page. And I think we can get them in here, and it's still pretty clear. Straight from the book. Nice to have everything on one page here. All right, so here's our two degenerate protons. That means they have the same energy before we put them in an environment where there's an electromagnet. Now you could read about electromagnets on your own. They're easily made. You just have a bunch of wires looping around thousands of times and run electricity through them. So you're forcing electrons to go in a circle, which causes a magnetic field. And the more loops you have, the more powerful your magnetic field that you create. So you get what you pay for with these machines that have these electromagnets in them. A more expensive machine will cause a bigger electromagnetic field. So I got two machines here. I have one machine with this electromagnetic field. I'm going to turn it on, and then these guys will no longer be the same energy because one of them will be stabilized by the magnetic field, the one with the spin oriented to give the same direction. And look at that, it got more stable. And the other one, which was misaligned with the electromagnet, got less stable, and it went up here. Anytime in science when you can create two different energy states, there will be an instrument that you can make that can detect these two different states. And what you will do now is you will tweak, or how about pulse this proton here with the exact amount of electromagnetic energy to cause it to absorb energy and then go from this spin, which would be counterclockwise, to this spin, which is clockwise. And after you've done that, after a very short interval of time, it's going to say to itself, I don't like being like this, and flip its own spin back. But you're continually pulsing it with that energy, the right amount of energy, to cause it to go back up here, and then it relaxes back, and you're going here and relaxes back. This is called resonance. You're going from one spin state to the other by applying the exact amount of energy that corresponds to the gap from here to here to cause the proton to switch spin to here, and naturally on its own it will come back. And all you have to do is monitor the amount of energy you put in and then see if it got absorbed. If it got absorbed, then a particular type of proton was doing the absorbing, and your machine would say, oh, this radiation got absorbed. It didn't make it through the other side of the machine. Therefore, there's a particular type of hydrogen in this molecule. This is the most useful information for analyzing molecules. The advent of nuclear magnetic resonance transformed organic chemistry more than any other physics developments that we ever borrowed or stole. Just trust me on this. We'll talk more about that later. Now, sometimes the difference in energies are very similar between hydrogens in a molecule that are only slightly different. We'll talk about what makes hydrogens different than each other in a molecule later. So if we only have a very small difference here and then another pair of spins in a different type of hydrogen are only a millimeter above here, you're going to have trouble deciding which is which. So if you spend a little more money and you turn on a bigger electromagnet, all your gaps get bigger, so it's easier to tell the difference between them. We call this resolution. You'll be able to tell the difference between the different spin states more easily. Okay, so if your energy gap here was, say, I don't know, 5 megahertz, and you used an electromagnet that was twice as powerful, then your energy gap would be 10 megahertz here. It's proportional to the amount of energy of your electromagnet. Okay, and I didn't tell you yet, but the energy required to go from this counterclockwise spin state to the clockwise spin state, the amount of energy you have to put in to start that resonance is in the radio frequency energy. That's our lowest energy frequency. So what we have is we have a radio transmitter as part of our machine, and it transmits individual frequencies, and we see which of those get absorbed, and the ones that got absorbed tell us what type of hydrogen we have. It's sort of like you have a receiver on the other side tuned into your favorite radio station, and if you get a signal, that means your favorite radio station is playing, and if you don't get a signal, it's not. All right, so moving on, let's look at the textbook some more. Let's just move the textbook over here. And here we are. We haven't got to our key, most important fact. We're going to just read this slowly together. It's worth taking some time. There's something that gets in the way of your electromagnet, and that's electrons. We know electrons are present in every molecule, right? So if electrons are closer to a hydrogen nucleus, they're going to partially block or shield the applied magnetic field. That's your big electromagnet. This will diminish the gap, the delta E. Remember the gap we saw was between the two spin states? That will be diminished if electrons are close by. So it will seem like there's less electromagnetic energy hitting the hydrogen. And conversely, when electrons are pulled away from a hydrogen, the nucleus is more exposed and it's going to get a bigger gap. So if you have a, let's see my hands here, if you have an electrons pulled away somewhere else in the molecule by, say, a fluorine, then the gap gets bigger because each hydrogen is able to feel the electromagnetic field better without those electrons in the way. The analogy I like to use is, let's just pretend we're listening to each other. It's a lot easier to listen to somebody beside you if there's nothing between you, right? So if you're talking to somebody normally compared to talking to somebody where there's a thin sheet between you, it seems a little muffled with the sheet there. Well, the sheet is electrons and they're partially blocking the sound. The analogy works for magnetic energy too. So let's start with a simple molecule. Ethyl fluoride, also known as fluoroethane, right here. There are H's here that are D-shielded. Why do I say that? Well, the fluorine pulls electrons away from the carbon in this bond because of its high electronegativity, and that exposes these hydrogens more to the electromagnetic field. These are less D-shielded, so they're more shielded in a relative sense because the fluorine's not anywhere near as close. So I want to remind you of the word inductive effect, because that's what we just talked about. Fluorine has inductive effects. It will pull electrons away from the carbon, and as a result, that pulls electrons away from the hydrogen. The closer you are to the fluorine, the stronger the inductive effect will be. And that causes the energy gap to get bigger. So it will take more energy for you to cause the spins to resonate from the lower energy to the higher energy. It's going to take more energy for that to happen. And our charts for NMR, nuclear magnetic resonance, they have units in the x-axis that depict how big the gap is in the energy. And it's parts per million, so that we can have different people with different machines, even if one's more a powerful electromagnet than the other, they can still have the same numbers to compare. What ppm is the ratio of the energy gap that we saw between the two spins. The energy gap, I'm reminding you, if it lets me move this, it's not letting me move this. Here we go. The energy gap here, the ratio of that to the power of the electromagnet multiplied by 1,000,000, because protons have very little magnetic fields. So to make the numbers make any sense, we have to multiply it by 1,000,000. This is a much bigger number down here, the power of the electromagnet. All right. So with the fluorine present, we get signals around 4.5 ppm. And this is a normal methyl for the most part, and that will give signals near 1 ppm. You don't have to memorize those things. Okay, so here's a little more information here. Here's your ppms. Ignore the shapes of these. That's another discussion which we'll do in the second segment, which is coming up real soon. First segment, we're going to just focus on where the peaks are. That's 1 out of 3 questions. We're going to get 3 questions for every proton every time. I'll outline the questions right now. Where is the peak is question 1. What pattern is the peak is question 2. And how big is the peak is question 3. Let's just focus on where is the peak. Where is the peak? We can predict that from table 13.1, which if you zip around a little bit, I got a blank page there. There's table 13.1. And you'll see a normal methyl has a peak somewhere near 1. And if there's a fluorine real close to, it's like it's on the same carbon, your peak will be around 4.5. You may have noticed already that this is on the back side of the periodic table every time you take a test in Chem242. So it's not something you memorize, it's just something you use. All right, so the where's the peak question has to do with things like inductive effects and other effects that we're not really going to get into because we don't need to. We're big on the practical application of NMR. So using that table instead of knowing why the numbers are what they are is more important to me. So to end our first segment here, we can predict just from looking at the molecule that we should see a peak near 1 for this kind of hydrogen, and all three of these hydrogens are identical. They're one set. So they'll have a peak in a certain location close to 1 because the table told us that. These two hydrogens will have a peak somewhere near 4.5 because the table told us that if there's a fluorine on the same carbon as the hydrogen, the peak will be around 4.5. This is a good spot to stop our first segment. And I'm going to do it properly so we don't have to call Leo this week. And I'll see you in 5 minutes.